We'll continue forward with kinematics today. Okay, so let's see last lecture. We've looked at various examples of relative motion, including the relative motion of rain with respect to a moving person, and relative motion of a swimmer with respect to moving water. Okay, so we will continue ahead with more examples of relative motion today. We are more or less done with the theory part of relative motion, but a few more types of applications and examples. And with that, we will conclude kinematics.
So, sir, today is the last lecture of kinematics, no?
Yes, last lecture. Maybe next lecture we will look at questions and doubts, but otherwise it is the last lecture of kinematics today. Next lecture we'll be starting with circular motion, but we might also do some questions, and especially if you have doubts from the module or HC Verma, we will discuss those also. So let's look at examples of application of relative motion.
Sir, kinematics 2 will be later on, right?
Relative motion is in kinematics too, beta.
Okay.
Relative motion questions are there in kinematics too. They are there in HC Verma exercise also, but very few in number. So mostly the relative motion questions you have to do from the module kinematics 2 chapter.
Okay.
Okay. So just looking at the basic concepts of relative motion, the relative position of one object with respect to the other is the position of that object in the ground frame minus the position of the other. So from this, the displacement, the relative displacement becomes again the difference of the displacements in ground frame. The relative velocity becomes the difference in absolute velocities or ground frame velocities, and the relative acceleration. Okay, so the formulae are very simple and symmetrical. So main thing is how to make use of this in example situations. So let's begin with another example of relative motion of rain with respect to a moving observer. So now we have this situation where due to a breeze or wind, rain is falling in a slanted manner. It's not falling vertically. Rain itself is falling. And there is a person moving on the ground horizontally. So when the person is moving with a horizontal velocity of, let's say, 3 kilometers per hour, the rain appears to be vertical to him. It appears to be falling vertically with respect to his reference frame. Now, if he speeds up to 7 kilometers per hour, so from walking at 3 kilometers per hour, he now starts running at 7 kilometers per hour. The rain appears to be at an angle of 45 degrees with respect to the vertical. So find the velocity of the rain with respect to a stationary observer. Or with respect to ground frame, what we say. And its angle with respect to the vertical. So previously we had seen a situation where rain was falling vertically and the person was walking horizontally. So in that situation, it was like this: if this is the velocity of the rain vertically, and if the person is moving at a velocity like this, then in this case, what happens is that the relative velocity of the rain with respect to the person can be understood by drawing this diagram. So relative velocity will be the velocity of the rain in the ground frame minus the velocity of the person. So this becomes that vector. Velocity of the rain with respect to the person becomes velocity of the rain minus velocity of the person. So that you can see in a vector diagram is like this, where these are the two vectors, velocity of the person and velocity of the rain. But that was in a situation where rain was falling vertically. Okay, this we have seen in the previous lecture. Now this is a slightly different situation. Here the rain itself is falling in a slanted manner. Okay. Here VR is slanted due to a wind or a breeze. Some kind of wind or breeze is blowing in this direction. So that is making the rain fall in a slanted manner. Its absolute velocity in ground frame only is slanted. Okay. So just follow the language of the question and modify this vector diagram as you require to do to adjust to what the question is asking for. Okay. So the interesting thing here is that the relative velocity appears to be vertical when the person's velocity is 3 kilometers per hour. So see how you have to adjust this vector diagram on the left hand side. Sorry, on the right hand side, how you have to adjust it for the situation on the left hand side. Yes, very good, Akshat. The answer is correct. Only the angle with respect to the vertical you have to check once. I think the magnitude of velocity you have calculated is correct. Yes, Siddharth, your answer is also correct in vector format. So let's understand this. So in the first case, the velocity of the person is of magnitude 3 kilometers per hour. And the velocity of the rain with respect to the person appears to be vertical. So when we draw the vector diagram corresponding to this, we'll see that if this is the velocity of the person, then the velocity of the rain must be something like this, so that the relative velocity appears to be vertical. This is 3 in magnitude. So in other words, in this diagram, this horizontal component of the rain's velocity, this must be 3. And this vertical component is something unknown. Okay. Now in the second case, what is happening? The person's speed is changing to 7 kilometers per hour. And the relative velocity of the rain with respect to the person now is at 45 degrees to the vertical. So the above diagram has to be adjusted in such a way that the person's velocity is changed from 3 to 7. This is now 7. And this new value of the relative velocity this appears to be at 45 degrees to the vertical. So in this now you can see this side is y and this side is 4, because this side here is x equal to 3 from above. This side is y. So in this triangle, now you can see that 4 by y is equal to tan 45, which is 1. So y is equal to 4. That means if we take the xy system like this, the velocity of the rain in the ground frame is 3 I cap minus 4 j cap. So it has a magnitude of 5 kilometers per hour. And this angle here, suppose this is theta. So this is at theta equal to tan inverse of 3 by 4 with respect to the vertical. Okay, so why we are taking tan inverse of x component divided by y and not y with divided by x? Because we are calculating the angle with respect to the vertical and not with respect to the horizontal. It is at 37 degrees with respect to the vertical.
So,
Yes.
can you explain that second diagram?
Yeah, in the second diagram, just the velocity of the person is increased from 3 to 7. No? Whereas the velocity of the rain is the same as in the first diagram. So the velocity of the rain is this way only, the same way it was in the first diagram. That's not changing. The rain is falling at the same velocity with respect to the ground frame, but the person's velocity is now increased from 3 to something greater than 3. So that is why the relative velocity now appears to be at an angle like this. Okay, is it clear?
Yes, sir.
Okay.
Sir, can you scroll up to the question for a second?
Yes.
Okay, sir. Thank you.
Okay. Okay. Now let's move on to an example of relative motion between a swimmer moving with respect to flowing water. That kind of situation
Sir,
again. Yes.
sir, can you scroll up for a second?
To the solution.
Yes.
Okay.
Done, sir.
Done. Okay. Now coming back to a situation where we have a swimmer or a boat moving across a flowing river. So that kind of example. So now the width of this river is D. Now what happens is that a swimmer starting from this point swims in this sort of direction relative to the water, where this angle is D with respect to the perpendicular. I mean, this angle is theta with respect to the perpendicular. So a swimmer swims at 8 kilometers per hour with respect to still water. In a river flowing at a speed of 4 kilometers per hour. Now, if he swims in the direction shown, at theta with respect to the perpendicular to the flow, is such that he moves along the line AB, which is perpendicular to the flow. Okay. So the net velocity of the swimmer now has to be perpendicular to the flow like this, because he moves, okay, with respect to ground frame. He moves along that line like this. So first of all, find the angle theta, okay, and the net velocity of the swimmer in the ground frame. And second is, if this distance is given to us as 3 kilometers, find the time taken from A to B. Now third part, if instead, okay, he swam along AB, that is at theta equal to 0 with respect to the water, okay, then find the time taken, okay, and the net displacement. What would be the net displacement in that case? So this third part is actually like the part we discussed in the last lecture, whereas the second part and the first part are with respect to modification, that instead of swimming perpendicular to the flow, he's swimming in a sort of diagonal direction in such a way, but he's adjusting that angle theta in such a way that his net velocity now should be along the perpendicular. His net velocity should be along the line AB, which is perpendicular to the flow velocity of the water. So here we'll be using the concept that the velocity of the swimmer in the ground frame is equal to the relative velocity of the swimmer with respect to the water plus the velocity of the water. So this is like the net velocity with respect to ground frame. This is the velocity with respect to water. This is the swimmer's velocity with respect to the water of the film, and this is the flow velocity. So this equation has to be used.
Sir, you are on mute.
Okay, so hope the application is clear to all of you. Yes, somebody had some doubt in this? You can see that you are adding this vector, the relative velocity vector, which is of magnitude 8, but at an angle of theta to your y-axis. You're adding this to your velocity of the water in such a way that the vector sum should now be along the y-axis. So the vector sum of this and this should be along the y-axis. So this is a condition for that. That its x component should become 0. So that's how we are getting the condition that if its x component is 0, we're getting this condition. So from that we are getting theta as 30 degrees, and once we got theta, you can see this is the net velocity. So that net velocity is this much, and therefore the time taken is much. So note this down quickly, people, the first and second part. Now in the third part, instead of the relative velocity being at theta like that, it is actually along the y-axis. So in that case, what will happen? The net velocity in the ground frame, that one will become diagonal, because it will become the vector sum of these two perpendicular vectors. So he'll end up moving in a diagonal sort of direction instead of moving in the perpendicular direction. The net velocity will be along a diagonal direction. So just adjust the vector diagram for that situation. Okay, let's come to that next situation now. So in this situation now, what is going to happen is that the net velocity is going to be at some acute angle with respect to the flow velocity, because the swimmer has directed his own velocity, the velocity with respect to water, along the perpendicular direction. So this 8 kilometers per hour vector is along the y-axis. So now the net velocity is the vector sum of this 8 j cap with the flow velocity, which is along the x-axis. So the net velocity of the swimmer will be along the diagonal to this rectangle. And so the motion of the swimmer will also be like this. His displacement will be in this sort of direction. So instead of reaching the point B from A, he will end up reaching the point C. Okay, the path will be AC. You have to find how much time he reaches here at, because he starts from here at t equal to 0. Just a moment, people. Yeah. So if he starts from here at t equal to 0, instead of reaching the point B, he will end up reaching the point C here. So this will be his net displacement at some time, which we have to calculate. So now you can see that the velocity of the swimmer with respect to ground frame Okay, so in this case now you can see that the net velocity of the swimmer will become the vector sum of these two. So it will become 4 I cap plus 8 j cap. So it will be at an angle theta like this, such that the magnitude of this net velocity is 4 root 5, that is square root of 4 square plus 8 square. Okay. And theta is equal to tan inverse 2. And now we can see that the displacement will be equal to this net velocity into time. So the displacement, if this is some unknown distance x, okay, and this is the known width, which is 3 kilometers. So this displacement will be that unknown x I cap plus 3 j cap, and this should be equal to 4 I cap plus 8 j cap into whatever time. So this is in kilometers. So when we open this equation up, we can see on both sides comparing, we get x is equal to 4t, where x is in kilometers, 4 is in kilometers per hour, so t is in hours. Okay. And we get the y component, which is 3 kilometers is equal to 8 kilometers per hour into time t in hours. So from the second one, from this one, we can see that the time is 3/8 of an hour. Okay. So that is how much now? 90 by 4, 22.5 minutes. Okay. And now we substitute that in the first equation. So we will get the value of x, the amount that he has drifted, that will be 4 multiplied by 3 by 8, or 1.5 kilometers. So the net displacement, which will now be square root of, okay, so this will be 1.5 square plus 3 square, that is 1.5 root 5 kilometers. Okay, so we will hope this question is clear. Okay, now we will move on to some more types of applications of relative motion. So relative motion between two projectiles or two objects moving under the action of gravity. So this is a very interesting situation. So anytime we have something like this where two objects have been projected, so it's moving like this, and simultaneously another object has been projected like this, let's say, but at the same time. So at some time, let's say B has reached here, and at that time A has reached here. Moving with some velocities like this. So here, if you look at this, at any time after projection, the acceleration of A is the same as the acceleration of B, which is acceleration due to gravity. So that means the relative acceleration of A with respect to B, or the relative acceleration of B with respect to A, whichever we choose to take, equals to 0. So this means that the motion of A relative to B, okay, or B relative to A, whichever we choose to take, is a uniform motion. So by uniform, we mean that it has 0 relative acceleration. So that means the relative velocity of A with respect to B at any time t equals to the initial relative velocity, which is equal to UA minus UB, okay, or vice versa. Okay. The velocity of B with respect to A at any time is equal to the initial velocity of B minus the initial velocity of A. So this tells us that A's motion with respect to B is with a uniform velocity, which is this thing. So in relative motion application, the concept is very simple. Okay, so it means that its motion relative to B is along a straight line with uniform velocity, doesn't have any acceleration. So this is a very important fact. Okay, all this over here. So this final part is very important because now we see, therefore it's very easy to solve the relative motion because it's happening without acceleration. It's happening with a constant velocity. So this fact makes it such that, you know, any problem we are solving where two objects are moving under the influence of gravity, it will be naturally much easier to solve it by using the relative motion concept. Okay. So just take down this concept over here and then we'll start looking at the typical examples of its application.
Sir,
Okay, so let us understand the application of this.
Sir,
Yes.
sir, is the velocity A respective to B is equals to velocity B respective to the initial one?
No, it is negative of that direction wise.
Okay, sir.
Relative velocity of A with respect to B is opposite to the relative velocity of B with respect to A. Magnitude will be the same, but the direction is opposite, right? Okay. So let's start with this kind of an example. What we are having now is that one object starts in free fall. So this guy drops a ball A. So at time t equal to 0. And simultaneously another person here throws another ball B, let's say, with a velocity like this at an angle theta to the horizontal. Such that this distance here, the vertical displacement between them initially is h, and the horizontal displacement between them is d. So simultaneously, at time t equal to 0, A drops a ball and B projects a ball as shown. Okay. Now, given that h is equal to 60 meters and d is equal to 80 meters and the initial speed is equal to 50 meters per second for this, show that if the angle of projection theta is 37 degrees with the horizontal, then the two will collide. Okay. And find the time t at which this collision will occur. So now a question like this, obviously the question doesn't say that use relative motion to solve. So it's up to you. You can solve the motion of the ball B in the ground frame as a parabolic path and the motion of ball A in the ground frame as a straight line path in free fall. And then find the condition for them to collide with each other and show that that condition is satisfied over here. But we also know that if instead of using that method, we try to look at the motion of the ball B in A's frame, or we look at the motion of ball A in B's frame, whichever of the two, then the problem should become comparatively simpler, because then instead of solving a curved path with acceleration and all that, we'll be just solving a situation where with respect to one object, the other object is supposed to move at a uniform velocity. Okay. So the hint here will be, if we use relative motion, it will be much easier to solve. The motion of B in A's frame, okay, or A in B's frame, is with a uniform relative velocity. Okay. So that makes it much easier to solve. Application. Whereas if you are solving in ground frame, then one of the objects is moving in that projectile parabolic path and the other is in straight line free fall. So it's more complicated. Okay, so just try this out. As I told you in the section above, the relative velocity of B with respect to A or A with respect to B at any point of time is the same as the initial relative velocity because their relative acceleration is 0. Okay, so let's see that concept here. So before we get into it, now let's try to understand how exactly that's going to work out. Okay, to show the condition. So if we are seeing the motion from ground frame point of view, then this is what we are going to see. In the ground frame, what we'll observe is that one object B starts from here at t equal to 0. Another object A starts from here at t equal to 0. So A falls vertically like this and B goes in a projectile path like this. So if they happen to collide, then at some point of time they should simultaneously be here. At some time t, B and A should be here. So this is like the collision condition. So we'll come to that. Okay, but now the more interesting thing is if we look at, so this is A and B as seen in the ground frame. Okay. But something little bit more abstract. Imagine we are stuck to A's frame. Okay. So the motion in A's frame. So in A's frame, what is happening is B is starting from here somewhere, okay, at t equal to 0, and it has a relative velocity like this. And the acceleration of B with respect to A is 0. So after some time, if they are colliding, then B should reach here at time t. And by the time B reaches here, now it's a little difficult to understand how this is happening, but this thing will make it easier. Now at t equal to 0, the ground was here. But if you're stuck on A, by the time B has come and hit you, the ground has also come closer. At t equal to t, the ground is here. Okay, so this is the concept. Okay, so if you look in this situation, what is happening? The velocity of B with respect to A at any time t, because it's a constant velocity, no? That is equal to the initial velocity of B with respect to A. That is the initial velocity of B minus the initial velocity of T. Now, initial velocity of B, you can see this was 50 meters per second. And we were to check the condition when we take the angle as 37. So this was we write it as a vector, it will be 40 I cap plus 30 j cap. So this is 40 I cap plus 30 j cap. And the initial velocity of A is 0. Okay, so the velocity of B with respect to A should be 40 I cap plus 30 j cap in meters per second. Okay. So now the thing is that if you can see in this diagram, what I'm saying over here, if B collides with A, okay, then the direction of this vector should be along the line EB, or rather BA. It should be along this line from B to A. It should be along this line, basically. Okay. So this line is such that this is 60 meters and this is 80 meters. So you can see that the line BA this is at an angle of theta such that so theta is equal to 37 degrees. So that is now the condition for this also. So that is why when we take this one's angle also as 37, that is a condition for it to collide. And therefore the collision will occur with at time such that this displacement so for collision so you can see that the time will be 2 seconds. So by using the relative motion concept, you can see that it has become a one-line solution. So this is the preferable method for solving any such problem involving the motion of two objects which are moving under the action of gravity. Okay, now let's verify this by the ground frame method. So in the ground frame, we can see that your projectile B at an angle 37 degrees. If it starts from here at t equal to 0 and A starts from here, so because this is 80 meters, this length, so you can see the time at which this projectile comes and crosses this time is, let's say, t1. So you'll see that the x component of B's displacement is u cos theta t. So that is 40 t. So 40 t1 should be equal to 80 meters. So you can see that this time is equal to 2 seconds from here. Okay. But we can also see that at this point of time, the y component of B's displacement, this one, the y component of B's displacement is u sine theta t minus half gt square. So that is 30 t minus 5t square, suppose, okay, taking g as 10. So at t equal to t1, which is 2 seconds, y component of B's displacement will become 30 into 2 minus 5 into 2 square. So that is 40 meters. So you can see that this is becoming 40 meters. Okay. At t equal to 2 seconds. So if A is also here at this point of time, then A's displacement, suppose A is here at time t2. So this total was how much? This total was 60 meters. So if A reaches here at the same time, then A's displacement should have a magnitude of 20 meters. So let's check whether that time t2 matches t1 or not. So if it matches, then the condition is satisfied for collision. So A's vertical displacement is half gt square. So at t equal to t2, A's vertical displacement should be 60 minus B's vertical displacement, which is 20. Okay. So 20 should be equal to half into g into t2 square. So you can see that t2 is coming out to be 2 seconds. Okay. So therefore, t1 equal to t2 equal to 2 seconds. So that implies that A and B collide. Okay. And they collide at what time? At the time of 2 seconds. Okay, so let's look at another example of this relative motion between two projectiles. Now this particle A this time is projected horizontally instead of dropped. It is projected horizontally at t equal to 0. It is horizontally projected at 10 meters per second, so that it goes on a path like this. And another particle B at t equal to 0 is projected with velocity of 40 meters per second, but at some angle theta, which we don't know. And additionally, what is given to us is that these distances, this vertical distance is 60 meters, and this time this horizontal distance is 40 meters. So A and B are projected as shown. We'll just make this 50 meters per second to be easier to solve. Just give me a moment. Make this different. We will make this 30 root 2 meters per second. So first of all, if theta is equal to 30 degrees, will A and B collide? And secondly, find theta such that collision occurs, and find the time. At which the collision occurs. So just try try this question out, people. Same kind of concept you can apply, same method. Just make a correction to this value also. This h should be 30 meters instead of 60 meters. Okay, h is 30 meters. This distance d is 40 meters. Okay, so anybody worked out the answer to this question? Okay, so again, you can see that the line joining A and B, this line, this is inclined at what kind of angle here? This is inclined at an angle of 37 degrees. So the condition for them to collide is that the relative velocity of B with respect to A, that should be along this line. Okay. So velocity of B with respect to A, which is basically the initial velocity of B minus the initial velocity of A, this should be along the line DA, this line. Okay. Now you can see that if you take your XY axis like this, you can see the initial velocity of B is 30√2 with a minus sign cos theta I cap plus 30√2 sin theta j cap, like this. And the initial velocity of A is 10 I cap. So the velocity of B with respect to A, this should become what? The difference of these two. So it will become minus of 30√2 cos theta plus 10 and plus of 30√2 sin theta j cap. So it's basically some minus Vx I cap plus Vy j cap. This is that relative velocity. So this vector, this should be along this line. Should be along this line such that this is 37 degrees. Okay. So that means this Vy component and this Vx component should have a ratio of tan 37 for this condition to be satisfied. So now just solve for this and you will get the answer. And that will also answer the first part, that if we keep the angle at 30 degrees, you will see, because you will calculate with what angle is required for the collision to occur. So you'll see whether or not 30 degrees satisfies that condition. So yes, no answer to the first part will come from that. And then for the second part, you'll know at what angle theta you want to project. So Vy is 30√2 sin theta and Vx is so this should be equal to so now we have to just solve for this condition. So in this equation, you can actually identify it directly that if theta is equal to 45 degrees, then sine theta is equal to cos theta is equal to 1 by root 2. And left hand side becomes equal to right hand side. So then the condition becomes that theta should be equal to 45 degrees. Therefore, the answer to the first part becomes theta equal to 30 degrees. It will not collide. They do not collide. And third part, the time at which the collision will occur will be the displacement of p with respect to a divided by this relative velocity. So once you got theta is 45, you can put it back here and you can find the relative velocity and you can compare it with the displacement. Okay, so now let's calculate the time. Anybody's done that? Okay, let's see. So when you substitute theta as 45, you can see that the velocity, the initial velocity of b actually becomes minus 30 I cap plus 30 j cap. And the initial velocity of A is already plus 10 I cap. So the relative velocity of B with respect to A becomes minus 40 I cap plus 30 j cap in meters per second. Okay. And for collision, the relative displacement of B with respect to A, what should that be? So that should be this displacement. This was 30 meters and this was 40 meters. So for B to reach A's location, it should make this displacement. This should be the displacement. So it should be minus 40 I cap plus 30 j cap in meters. So from this, you can see that time will be 1 second. So if you project this at an angle of 45 like this, and while you're projecting A horizontally at 10 and B at 30√2 meters per second, but at 45 degrees, what will happen is that this will come like this and this will come like this, and somewhere in between they will collide at t equal to 1 second. So that is the conclusion of this question. You can also verify it by solving the individual projectile motion in ground frame. I will not get into that in this class here today. Okay. So with this, we are done with all the concepts and various types of applications of relative motion. You should be in a position to solve anything and everything to do with kinematics from this point onwards. So next lecture, we will do a few example questions from the Kinematics 2 module, Kinematics 2 chapter in module 1, as well as the last few questions from H.C. Verma, which are also slightly tricky. But after doing that in the first few minutes, maybe 40 minutes or so of the lecture, we will move on to circular motion, which is the next chapter. So next chapter for us will be circular motion. That's it for today's session, people. Wish you all the best. Have a nice day.
Awesome.
Thank you.
Sir,
Yes, Tanay, the chapter is completed, Beta, just for your information. Okay. You can complete the problems now and we'll discuss the doubts. But the
So, sir, I
chapter of
was just asking
kinematics,
that. So, like, when will, like, after solving all the questions, when will the this chapter get over, sir? When will we start the next chapter?
next lecture. Next lecture, we will start circular motion.
Okay, sir.
About half the lecture, we'll discuss doubts and questions. It should be enough time, 40-50 minutes. And
Yes, sir.
after that, we will start circular motion.
That was what was I asking. That how much time will we get for?
Right. So whatever time is required, but I think about maximum 1 hour will be enough. Okay.
Okay, sir. Thank you.
Yeah. Anybody had any other doubt, any other question?
sir, kinematics 2 is variable acceleration, right?
There are questions of variable acceleration also and relative motion also, both the things.
Okay. Okay.
Yeah.
So, sir, will we do it after circular motion?
No. Kinematics 2 is done better. So what we have done here, relative motion is only kinematics 2. And variable acceleration we have seen in the calculus portion of kinematics earlier now. So it is those applications only.
Okay, sir, understood.
So all these river water type of problems and all these relative motion problems, that is only there in your kinematics 2 chapter. Okay.
Okay, sir. Sir,
Yes.
sir, can you please send the recordings of lecture 9 and 10 as I am unable to find them on YouTube?
Okay, I will send the links of that. Okay.
Okay, sir. Thank you, sir. Bye, sir.
Okay.